Swayam Prabha. Digital India. Educated India.
So we are now in our second lecture, that is linear programming basic concepts. Linear programming basic concepts, essentially we had already discussed that linear programming is about programming, that is allocation of resources to activities. Activities are basically kind of decision variables, and those decision variables are basically they are decided with respect to availability of certain resources. So how much resource should be allocated to activities so that some objective function can be either maximized or minimized. Now, we can have an unconstrained problem where there are no constraints, but usually all linear programming problem, they are having certain constraints also. But very name suggests that the objective function as well as the constraints are all linear, and the activities are also non-negative. So for solution purpose, it is very important that they should always be non-negative. That means they should be greater than equal to 0. And as I have already said, that activities are represented by the decision variables. Now, usually what happens that since resources are scarce in nature, one or more of the resources, they actually become the bottleneck resources. So because of these bottleneck resources, we know we have that some of these variables, they actually have, their values are restricted, right? So we cannot get as many as we can, and that is where we have to maximize or minimize the objective function. How can we best utilize the resources so that the objective function values are the best possible, and the decision variables, that is the xi's, they have the optimal values. And as I said that both the constraints and the objective functions, they are all linear. Now, the linear programming problem in the maximization problem, particularly in the standard form, they have these kind of constraints. The objective function maximize z equal to c1 x1 plus c2 x2 plus c3 x3 c4 x4, and constraints could be a11 x1, a12 x2, a13 x3, like that. So this should be a12 and plus a14 x4 less than equal to b1, then a21 x1, a22, etc. So like these, and as well as there are non-negativity constraints. Here these CIs, the C1, C2, C3, C4, they are all the profit coefficients. The x1, x2, x3, x4, they are like our decision variables or the activities. The constraints, in the constraints, the a11, a12, a13, etc., they are the coefficients. And these b1, b2, b3, the small b's, they are actually the resources. So there are 3 resources and the quantities available are b1, b2, and b3 respectively. And then we have the non-negativity constraints, that x1, x2, x3, x4, they are all greater than equal to 0. Now, having said that, we can have the maximization problems and the minimization problems, and in a standard form, the maximization problem that has got a maximization objective function, and the constraints are all less than equal to type, and also obviously the non-negativity constraint. So this is the maximization problem in a standard form, that is maximize z equal to sum over j equal to 1 to n cj xj, subject to sum over j equal to 1 to n aij xj less than equal to bi. Bi is the availability of resources for all I 1 to m and also xj greater than equal to 0 for all j equal to 1 to n. So this is the maximization LP problem in standard form. Similarly, we can also have minimization LP problems, and standard form they will be minimize z equal to sum over j equal to n cj xj subject to sum over j equal to 1 to n aij xj greater than equal to bi for all I equal to 1 to m, and also xj greater than equal to 0 for all j equal to 1 to n. So where is the difference? The difference is that maximization problem usually have less than equal to, and minimization problem has greater than equal to kind of constraints. But that is about standard form. If you compare the linear programming standard forms, you can see that objective function maximization and minimization, constant type less than equal to and greater than equal to, but the variable types are all greater than equal to 0. So this is the standard form. But in reality, the linear programming problem could be in non-standard form as well. So irrespective of maximization or minimization problem, the constant types could be less than equal to, greater than equal to, or equal to, and the variable types could be greater than equal to 0, unconstant in sign, or less than equal to 0. In maximization problem, since the usual type is less than equal to 0, so that is given first, and in minimization problem is greater than equal to, so that is given first. So we can, as like we have the linear programming problem in standard form, linear programming problem in reality can definitely be there in the non-standard form. So what can vary is all details are given here in this particular table. Before we move over, let us see some basic characteristics of linear programming. So first characteristics is linearity. See, what is linearity? Linearity essentially means moving in a straight line. That means things are proportional to one another. Say, for example, the objective function. Suppose the objective function is maximize z equal to 2x1 plus 3x2. First of all, you observe why it is linear, because there are no higher order terms. We don't have any x square or x cube or x to the power 4 terms. We do not have any logarithmic or exponential or if then else kind of terms. And if profit for 1 unit is 2 for a particular activity, then profit for 2 units will be 4. So it is all proportional. So there is a proportionality that is maintained. Fixed cost is not available. So that is about the linearity of the problem. The second thing is about the additivity. So what is exactly additivity? That profit or the use of resources, there is no interactiveness. So you see, sometimes what happened that I have two products. So if I make 2 units of product 1, then 2x1, so 1 unit profit of 2, 2 units profit of 4. But there is a second product also. Sometimes what happened that if I make sell more chairs, then selling table may become difficult. So there, if we make more profitability with chair, getting profitability with tables actually doesn't happen. Isn't it? So if I sell 2 tables, I may get profit of 6, but if I sell 3 tables, I may not get profit of, in that proportion. Now we are assuming that such kind of difficulties are not there. We really have additivity. That means profits of the 2 products can actually be added. So this is the essential idea of additivity. The divisibility essentially means that there are no integer solutions. So if you are making tables and chairs, 7.2 tables and 8.31 chairs, they are perfectly acceptable. You may be thinking that what is it, fractional number of chairs and tables, fractional number of people, why should we accept them? If we are not interested in accepting such solutions, then we say that the divisibility assumption is not true. So therefore, we have to have what is known as integer solutions. Now these integer solutions will be available when you cannot use the standard simplex procedure that we normally use for solving linear programming problem. We have to have some special kind of methods such as the branch and bound methods or integer linear programming methods if the divisibility assumption is to be relaxed. Is it all right? The finiteness basically says that we have a finite solution space. There are definite upper and lower bounds to the solutions and those kind of scenarios. Finally, the deterministic, that we don't have any probabilistic values. All the coefficient values are constant values. They are not varying. After that, we talk about a feasible solution space. What is a feasible solution space? Any solution that satisfies all the restrictions is called a feasible solution. So there are several constraints. Now, out of all these constraints, the solution that we get are called the feasible solutions. That means that satisfies all the constraints or the restrictions. And a feasible solution that satisfies the objective function is known as the optimal solution. So what is the optimal solution? Out of all the different feasible solutions, the best value that is returned, that is known as the optimal solution. Obviously, if it is a maximization problem, it should be the best possible value. If it is a minimization problem, it is the least possible value. Now, better than optimal but infeasible solutions may exist. So there could be solutions they are better than optimal but infeasible. So that means they are better than the current optimal solution, but they are not satisfying all the constraints. So there is what is known as a feasible solution space. Right. Now, linear programming solutions. So look here. Now, first of all, any specification of values for the decision variables is called a solution. So supposing I have two variables x1 and x2. Now x1 equal to 20 and x2 equal to 50 is a solution. X1 equal to 5,000, x2 equal to 9,000 is also a solution. So everything is a solution which actually is a specification of values within the domain of the decision variables. A feasible solution is solution for which all the constraints are satisfied. That's a feasible solution. An optimal solution, a feasible solution for which the objective function is most favorable. Right? Then we can have a boundary equation where less than equal to or greater than equal to signs are replaced by the equal to sign. Then we have what is known as a boundary equation. Usually the solution space boundaries are written by boundary equations. So most of the graphical things that we shall be attempting, we shall be writing the boundary equations. The corner point feasible solutions is a feasible solution that does not lie on any line segment connecting two other feasible solutions. So you see, supposing it cannot be an in-between solution. It has to be at one end. All right. So that are basically corner points in a sense that two constraint lines where they cut is a corner point solution, but it has to be feasible as well. Now, two corner point feasible solutions are adjacent if the line segment connecting them lies on the boundary of the feasible region. So these I'll explain them with some graphical solution that will be easy to understand. So let's take a simple problem. So here is a very simple problem. Consider a product mix problem. A company produces two products, chairs and tables. Wood is required to produce them. 6 units of wood is available. A company needs 1 unit each to produce a chair or a table. And the demand of chair in a day is 4 units. And the demand of the table in a day is also 4 units. And if the profit per chair is rupees 2 and that of a table is rupees 3, how many chairs and tables should be produced in a day so as to maximize profit. So very simple problem. Let us see how we go ahead with solving this. First of all, we have to define two variables. What should be our variables? Very clear that one is x1, which is the number of chairs to be produced. Other one is x2, the number of tables to be produced. So those two unknowns. What is the objective function? Maximize z equal to 2x1 plus 3x2. Why? Because rupees 2 is the profit per chair, rupees 3 is the profit per table. Now, what should be some constraints? First constraint is demand of a chair is 4 units. So that means x1 should be less than equal to 4. And demand for table is also 4 units. That means x2 should also be less than equal to 4. Now wood is required to produce them and only 6 units are available. And 1 unit of wood is required for a chair or a table. That means x1 plus x2 should be less than equal to 6. So this is what is written here. The decision variables x1 is the number of chairs produced per day. X2 is the number of tables produced per day. Objective function is maximize z equal to 2x1 plus 3x2. Why? Because profit per chair is rupees 2. Profit per table is rupees 3. So therefore maximize z equal to 2x1 plus 3x2. That is the objective function. And what are the constraints? As I discussed, x1, that is the number of chairs, less than equal to 4. x2 less than equal to 4. x1 plus x2 less than equal to 6. Why x1 plus x2? Because to produce 1 unit of x1, we need 1 unit of wood. And same thing for x2 also. So 1x1 plus 1x2, that is x1 plus x2 less than equal to 6. We also added the non-negativity constraints, that is x1 greater than equal to 0 and x2 also greater than equal to 0. So this is the very simple, the first stage, that is the formulation of the particular problem. Now suppose we want to plot this on a graph. How does it look like? So this is what has been done. So you see, if this is the x1 axis and this is the x2 axis. So what is the value of x1 along x1 axis? As we go further, x1 values are increasing, but x2 values are all zeros. So you can say that this line represents x2 equal to 0. Similarly, the x2 axis represents x1 equal to 0. Then we have 3 more lines. What are those 3 lines? x1 equal to 4, x2 equal to 4, and x1 plus x2 equal to 6. So what has happened, if you look at it very carefully, you will find that since x1 is less than equal to 4 and this line is x1 equal to 4, so this portion is going to be the domain of x1 less than equal to 4, this portion, this portion, because you put 0, 0, 0, it is satisfied. Since it is satisfied, it is this side. Similarly, about this line, it is this side. Similarly, about this line, that is x1 plus x2 less than equal to 6, it is this side. So out of all these sides, the common area, this is our common area. So this common area is the feasible solution space, which actually satisfies all the constraints. That means all points within this feasible solution space is a feasible solution. So that is why it is called feasible solution space. So you see, not only this point O or point A or point B or point D or point E, these are the 5, they are corner points, they are feasible corner points or corner point feasible solutions. And this entire thing is our feasible solution space. But you see, these 5 are not the only corner points. There are other corner points in the solution space also. For example, C, where the x1 equal to 0 line and x1 plus x2 equal to 6, they have cut. Then we have another corner point F and another corner point G. So I'll ask you a simple question. Are there only these 1, 2, 3, 4, 5, 6, 7, 8 corner points, or there could be more corner points available in this particular diagram? Think very carefully. You know, you are going to have two more corner points. What are those two corner points? Look here. These x1 equal to 0 and x1 equal to 4, they are actually parallel. But if they are not parallel, you know, they would have cut in somewhere. That point is another corner point we would have obtained. Since these two lines are parallel, that corner point is absent. But technically we can say that that corner point lies at infinity. Similarly, there is x2 equal to 4 and x2 equal to 0. You know, that also going to be another corner point. So in total, we are going to have as many as 10 corner points in this particular problem. Very interestingly, why we got 10 corner points? Are we not going to get something more or something less? Is it that there will be exactly 10 corner points given the constraints that we have considered in this particular problem? These are interesting questions. We shall try to revisit this question as we move further. Now look here. A very important concept is that the feasible solution space is convex. The convexity of feasible solution space is extremely important for solving linear programming problem. Now, what do you mean by convexity? Basically, if we take any 2 points P and Q within the feasible solution space and join them by a straight line, that straight line will be completely within the feasible solution space if the solution space is convex. So you try taking any 2 points within the solution space. For example, take one point here and another point here, join by a straight line. You see that straight line will be entirely within the solution space. Now this is happening because the feasible solution space is convex. See, we are not going to go in any kind of proof, but just trying to tell you that if the constraint lines are all linear and they together confine a solution space, that solution space is going to be what is known as a convex solution space. And that convexity of the solution space is a very important concept. You see, this convexity of the solution space, why it is so important? It is so important because it will lead to that the optimal solution would lie at one of the corner points. Now question is, why does it happen? Why does it happen that the optimal solution can be found at one of the corner points? See, you might have already solved such kind of problems earlier. There you have seen that to find the optimal solution, all we have to do is we have to simply look at these corner points of the feasible solution space. That is at O, at A, at B, at D, at E, and see which one is the best. And that is going to be our optimal solution. But the question is why? Why is it optimal? To understand that, we have to go a little further. So you see, a linear programming problem will always have a convex feasible solution space. This is because the objective function and the constraints are all linear. Obviously, for the solution space, we have not yet talked about the objective function. If the constraints are all linear and they bound a solution space, it is always going to be convex. Once again, how to know that this is convex? You just take 2 points, P and Q, any 2 points within the solution space, join them by a straight line and see that this particular straight line will be completely within the solution space. Right. So that's what is the thing that we have already understood. Now, next is that why the optimal solution is one or more feasible corner points. Let us take the profit line. What is the gradient of the profit line? The profit line is 2x1 plus 3x2. See, this is the profit line. How to draw it? Very simple. You take a particular profit. Say for example, this particular line, how can we get it? Say for example, that point B, we know this point is 40. All right. So if profit is equal to 40, that means profit at that point should be 8, isn't it? Because at 40, it is 2x1 plus 3x2, x1 equal to 4, x2 equal to 0, gives a value of 8. So if any profit line goes through the point B, which is actually 40, it has to be the profit, total profit has to be 8. Now put x1 equal to 0. If you put x1 equal to 0, then x2 you will get 8 by 3. So on the x2 axis, you plot 8 by 3 and then join these two, 8 by 3 and these 4, 0, 0, 8 by 3 and 4, 0, you join. Then that particular line, on that line, on every point, the profit will be 8. Now, what is the profit in this line? It's very clear because it passes through the origin. The origin value is 0, 0. If I put 0, 0 in the profit line, it is going to be 0. That means here the profit is 0. As the profit line moves parallel to itself, away from the origin, in the first quadrant, the profit goes up. Here it is 0. Here it is 8. So as the profit line moves parallel to itself, the profit goes up. The very nature of the curve is that it's a convex curve. So because it's a convex curve, which is a convex curve? The solution space is a convex curve. Because of that, as we move the profit line, when the profit line just moving out of the solution space, it will touch at a single point. Here in this case, it has touched at point D, right? So that is what is written here. As the profit line moves up parallel to itself, the objective function value improves. Finally, it just touches the feasible solution space at point D, right? It touches the feasible solution space at point D, and this is possible because the feasible solution space is convex. That convexity is very important. Suppose it is concave, it is that kind of shape, then you can still move further, isn't it? So this is not going to happen. It won't touch one single corner point when it moves out of the solution space. That means profit can be maximized when the profit line is cutting one of the feasible corner points, right? So that is why in linear programming, the solution is found at one of the corner point feasible solutions. Some special cases can also happen. What is that special case? Suppose this profit line, this red line, is actually parallel to this line CF. Suppose it is parallel to the line CF, what will happen? At the extreme point, the profit line will merge with CF. At that time, both D and E, both the corner points would be optimal. In fact, not only D and E would be optimal, but all points within the line DE also will be optimal. After that, the profit line will leave the solution space. So sometimes we can get more than one corner points as the optimal solution, particularly when the profit line is parallel to one of the bounding constant lines. So that also could be happening in certain situations. Nevertheless, the important thing to note here is that the linear programming problem has a very special property. The property is that the feasible solution space, once we get it, we know that optimal solution will lie at one of the corner points of the feasible solution space. In other words, when solving graphically, a feasible a corner point feasible solution is going to be our optimal solution. Now this is very important. That is what is written. Optimal solution is one or more feasible corner point solutions. It is one when the profit line is not parallel to one of the bounding lines, and it is more than one when it is parallel to one of the bounding lines. So once we know that, the profit line returns the maximum objective function value at one or more corner points of the feasible solution space. Hence, we can say that the optimal solution lies at one or more feasible corner points. Why one or more? Because when the profit line is parallel to a bounding constant line, we may get more than one optimal solution. Let me repeat that once again. Let us say that the red line or the profit line is parallel to the line CF. What will happen? Just before leaving the feasible solution space, the profit line will touch both point D as well as point E because it is parallel. So what will happen? After that, it will leave the solution space. So therefore, maximum value will be returned both point D and also at point E. Is it not? Since that is happening, you can say not only D and E, all points connecting D and E within that straight line are also going to be optimal. So those are some special cases when profit line is parallel to one of the bounding constraint lines. In other situations, it will simply touch one of the corner points and it will be like a tangent to the solution space. And therefore, that particular feasible corner point will be our optimal solution, right? So we understood this, and once we understood, it is very easy to find optimal solution from linear programming. So you see what we achieve if the objective function is linear, if the constraints are linear, we simply know we have to look at the feasible corner points and the solution will lie at one of those feasible corner points. So look here, solution space here is OA, DEB. At O, the value is 0. Why 0? Because this point is x1 equal to 0, x2 equal to 0, and therefore z equal to, what is our profit function? Maximize z equal to 2x1 plus 3x2. If I put it, we'll get 2 into 0 plus 3 into 0 equal to 0. At point A, it is 0, 4. x1 equal to 0 and x2 equal to 4. So what is the value of z? Z here is 2 into 0 plus 3 into 4, that is equal to 12. Alright, so at point A, the value is 12. What is the value at point D? It is 2, 4. That means x1 equal to 2 and x2 equal to 4. Alright, so how did we get 2, 4? Because this line is x1 plus x2 equal to 6 and this line is x2 equal to 4. So they cut at x2 equal to 4 definitely. So if we put x2 equal to 4, we get x1 equal to 2. So D value is 2, 4. And Z value will be 2 into 2. Why 2 into 2? Because 2x1 plus 3x2, x1 equal to 2, x2 equal to 4. So value at point D is 2 into 2 plus 3 into 4 equal to 16. What is the value at E? Value at E value is 4, 2. Why 4, 2? Because it cuts x2 equal to 4 line and x1 plus x2 equal to 6 line. Since x2 equal to 4, we can put that x2 equal to 4 here and we can get x1 equal to 2. So that value should be, E should be therefore, and I'm sorry, x1 4. And if x1 equal to 4, then x2 should be 2. So this value is 4, 2 and the value of z is 14. Finally, the point B, which is 4, 0, the value of z equal to 8. Now, out of all the different values of objective function, the 16 is the highest. So therefore, D is our optimal point and the solution to this very simple problem is going to be x1 star equal to 2. That is the optimal solution, x2 star equal to 4 and z star equal to 16. So we already knew all this, right? Before even studying this subject, you already knew that how to find out solutions to the linear programming problems graphically. Basically, draw the lines, find the feasible solution space, look at the corner points, and the solution lies at one of the corner points. So that part is very well known. The problem comes, suppose you cannot draw the graph. Now question is, you may ask why I cannot draw the graph. You see, we are having only 2 variables. Just for the sake of thinking, assume there are 3 variables. If there are 3 variables, then you cannot draw a plane graph. Then you have to draw a 3-dimensional graph. You may still think, okay, let me draw a three-dimensional graph. Somehow you may be able to draw a three-dimensional graph. It is difficult, but it is not impossible. Suppose you have 4 or 5 variables. Look here, you have 5 variables. Then your graph will be 5-dimensional. Look here, it is impossible or very difficult to really draw a 5-dimensional graph, isn't it? And suppose there are so many constraints. So with different kinds of lots and lots of constraints and many variables, it is not possible to always draw a graph. So if I'm not allowed to draw the graph, how can I find out solution to such problems, right? So you see the difficulty arises when number of variables are more, when the number of constraints are more, graphical solutions are not possible. But then the basic philosophy still remains. What is that basic philosophy? We have to get the feasible solution space and we have to find the corner point feasible solutions. There will be definitely many more. In this simple problem, there are 5 corner point feasible solutions. In a more difficult problems, there will be many more corner point feasible solutions. But still, they are finite numbers, and we know one of them is going to be an optimal solution, right? So because that happens, therefore, how exactly we can therefore quickly find the corner point feasible solutions, evaluate them and find the optimal solution. That is what we have to understand. To understand that, we bring a new kind of concept, that is going for an augmented problem. But I'll come to augmented problem, but before that, certain terms. Here are certain terms already I might have discussed them, but just quickly repeat them once again. Solution, any specification of values for the decision variables within the domain. A feasible solution, a solution for which all the constraints are satisfied. Optimal solution, a feasible solution for which the objective function is most favorable. Boundary equation less than equal to or greater than equal to signs are replaced by the equal to sign. Corner point feasible solution, a feasible solution that does not lie on any line segment connecting two other feasible solutions. And two corner point feasible solutions are adjacent if the line segment connecting them lies on the boundary of the feasible region. So these you already know. So let's look at the augmented problem. Now we are moving towards simplex. So what exactly is happening? Look here. The original problem was one of inequality. What was that? Maximize z equal to 2x1 plus 3x2 subject to x1 less than equal to 4, x2 less than equal to 4, x1 plus x2 less than equal to 6, non-negativity constraints x1 greater than equal to 0, x2 greater than equal to 0. What we are doing, we try to replace the less than equal to constraints by the equality constraints. To do that, we have to add more variables. So what exactly we did? We have considered 3 more additional variables. Now, what are these 3 more additional variables? X3, X4 and X5. They are the slack variables. Remember, these 4, 4, 6 are the nothing but the resources. So sometimes these variables are called slack variables. You can be also called as unused resources, or they can also be called a fictitious product for which only one unit of corresponding resource is required. That means X3 requires only one unit of these resource and none of the other two. Same thing about X4 and X5. X4 needs only these resource and none of the other two. X5 requires only these resource and none of the other two. So that will now have another problem. So this is the original problem. This is the augmented problem. Look here, once the augmented problem is formulated, now there is no difference between one variable from the other. It is simply a 5 variable problem written in a particular form. And that form is called a canonical form. What is canonical form? I shall discuss little later. but before that, let me show you the augmented problem in very clear manner. So maximize z equal to 2x1 plus 3x2 plus 0x3 plus 0x4 plus 0x5. Subject to x1 plus x3 equal to 4, x2 plus x4 equal to 4, x1 plus x2 plus x5 equal to 6. And non-negativity constraints x1, x2, x3, x4, x5 all are greater than equal to 0. Now interesting thing is that how many constraints are there? See, we have now 3 constraints and all are equality constraints. How many unknowns? There are 5 unknowns. So 5 unknowns and 3 constraints. Can we solve? Answer is no, we cannot solve. Alright, so what exactly we have to do? We have to therefore put excess variables to zeros. These excess variables we are calling as non-basic variables, and other variables we are calling as basic variables. So supposing here there are 5 unknowns and there are 3 equations, so 2 are going to be excess variables. So let's say which 2 are most easy to put zeros so that some solution can be found. Look here, x3 is there in only one constraint. So if I put x1 and x2 equal to 0, then automatically a solution very quickly we can write x3 equal to 4, x4 equal to 4, and x5 equal to 6. But let's go back to that graph once again. You see in this graph, which is the point which is x1 equal to 0 and x2 equal to 0. Can you see it is the origin? So this is the origin, and this origin will be the solution. This will correspond to that particular solution where x1 equal to 0 and x2 equal to 0, x3 equal to 4, x4 equal to 4, and x5 equal to 6. Is it not? So if I put x1 and x2 equal to 0, I get x3 equal to 4, x4 equal to 4, and x5 equal to 6, right? So you see, that kind of solution is called a basic solution. So how many basic solutions are we going to have? There are 5 constraints and there are 5 unknowns and there are 3 constraints. So 2 are put to zeros. Out of 5, 2 can be put to zeros in how many ways? It's very simple mathematics. 5C2. How much is 5C2? 5C2 equal to 10. You know very well that 5C2 equal to 5 into 4 divided by 2 into 1 equal to 10. So, 2 variables can be put to zeros in 10 different ways. And therefore, since these solutions are called basic solutions, can you see that we are therefore going to have 10 basic solutions? Is it not? We are going to have 10 basic solutions. So, what are those 10 basic solutions? See, if you look here, see, in a sense, x1 plus x2 plus some variable equal to 6. So you see, what are our constant lines? You see, this is x1 equal to 4. What we said that x1 plus x3 equal to 4. Here x2 plus x5 equal to 4. x1 plus x2 plus x6 equal to 4. But on this line x1 equal to 4. So on this line x3 equal to 0. Now on this line, since x2 plus x5 equal to 4 and x2 equal to 4 is this line, so can we alternately say that this line is nothing but x5 equal to 0? Similarly, this line can also be said as x6 equal to 0. So if you look at this graph in a different light, this graph can also be seen as, having 5 different lines. This line is x1 equal to 0. This line is x2 equal to 0. This line is x3 equal to 0. This line is x4 equal to 0. And this line is x5 equal to 0. So let's go back to that, augmented problem and look here. x1 equal to 4 means x3 equal to 0, x2 equal to 4 means x4 equal to 0, and x1 plus x2 equal to 6 means x5 equal to 0. And obviously x1 equal to 0 and x2 equal to 0 are the two axes. So you see the graph that we had, this graph is nothing but bounded by 5 lines, x1 equal to 0, x2 equal to 0, x3 equal to 0, x4 equal to 0, and x5 equal to 0. So the basic solutions, which are basically obtained by putting two of those variables to zeros. So you see x1 0 and x2 0 cuts at O, x1 0 and x3 0 cuts at infinity, x1 0 and x4 0 cuts at A. Similarly, you see these 5 can cut between themselves at 10 different points, and therefore the basic solutions that we are going to have, those basic solutions will actually correspond to the corner point solutions. So you see, in the original problem, we are having the corner point solutions. In the original point, some of them are feasible. In the augmented problem, we are going to have the basic solutions, and some of them are feasible, which are going to be called as basic feasible solutions. So they actually will correspond. So, what exactly I'm saying is that this is the augmented problem. It has got 5 unknowns and 3 equations. To solve them, 2 of them are to be put to zeros. Those 2 can be called as non-basic variables, and the solutions that obtained can be called for those variables as basic variables. Basic variables can be chosen in 10 different manners. So 10 different solutions can be obtained. Those solutions can be called as basic solutions. Some of them will be feasible. They are called basic feasible solutions. And these basic solutions will correspond to the corner point solutions in the graph in the original problem. And the basic feasible solutions will correspond to feasible corner point solutions. So this is the great advantage of linear programming. Look here, once we get the augmented problem, all we have to do is, take some slack variables and get equations and then find the basic solutions. Now you see, out of those basic solutions that are obtained by solving these equations, they also have to fulfill the non-negativity constraints. Those actually fulfill the non-negativity constraints out of the basic solutions. They are called the basic feasible solutions, and they correspond to the corner point feasible solutions. Since it is so, can we say therefore one of the basic feasible solution is also an optimal solution? So this is exactly what is been written here. If there is exactly one optimal solution, it must be a corner point feasible solution. If there are multiple optimal solutions, then at least 2 must be adjacent corner point feasible solutions. There are only a finite number of corner point feasible solutions. If a corner point feasible solution is better than all its adjacent corner point feasible solutions, then it is optimal. And here are the basic things: that augmented solution for the problem in inequality form that has been augmented by the corresponding values of slack variables for the problem in equality form. Basic solution and augmented corner point solution. So in an augmented problem, by putting the excess variables to zeros, the solution that you obtain is a basic solution. And what is a basic feasible solution? Augmented corner point feasible solution is a basic feasible solutions. Basic variables, remaining variables after setting the defining non-basic variables to zeros. And basic feasible solution, a basic solution where all basic variables are non-negative, right? So once again, the basic solutions are obtained by putting excess variables to zeros, and it corresponds to the corner point solutions of the original problem. We get the basic solutions from the augmented problem, and by applying the non-negativity constraints, we actually get the basic feasible solutions also. So a quick repeat. Let me go back to that graph once again. So you see we have this problem, maximize z equal to 2x1 plus 3x2 subject to x1 less than equal to 4, x2 less than equal to 4, x1 plus x2 less than equal to 6, non-negativity constraints x1 less than equal to greater than equal to 0, x2 greater than equal to 0. Then we plot them in a graph, and in this graph we find that the bounding, the boundary constraints are x1 equal to 4, x2 equal to 4, and x1 plus x2 equal to 6. They cut these three lines along with the axis lines, that is x1 equal to 0 and x2 equal to 0. They are supposed to cut at different corner points. Essentially, there will be 10 such corner points. Those 8 of them could be easily found, remaining 2 are at infinity. They are actually called the corner point solutions. Now, out of those corner point solutions, some of them are feasible, not all of them are feasible, and those which are feasible, that actually satisfies all the constraints, they form a solution space that is called a feasible solution space. The feasible solution space is convex. Convexity is known by if we take 2 points P and Q within the solution space and join them by a straight line, the straight line should be entirely within the solution space. That is what is known as the convex solution space. And if it is a linear programming problem, it is always going to have a convex feasible solution space. This is because the objective function and the constraints are all linear. Is it not? So when the constraints are all linear and as well as objective function is also linear, we are always going to have a feasible solution space which is convex in nature. Now, because it is convex in nature, if the profit line moves parallel to itself up, finally it will touch at exactly one point, or it will merge with one of the bounding constraint lines, and at that point the profit value will be maximum. So therefore we say that optimal solution will lie at one of the corner point feasible solution. So we can as well say that, and that will actually give us a tremendous advantage. And that advantage is that to get the solution, all we have to do is we have to find one of the corner points only. And when the solution, the profit line is parallel to one of the constraint lines, at that time we are going to get multiple optimal solution. So exactly this is what has happened, that feasible, corner point feasible solutions, 5 in number, they are evaluated. The best one is point D. So point D has come up to be our answer. Thereafter, what we did, we written the augmented problem by turning the inequalities into equalities, by adding more variables, and those variables are added in such a manner that they are in a canonical form. What is the canonical form? The variables that we have added, the slack variables, those slack variables are added one at a time. That means one slack is added with a coefficient of 1 with the first constraint, only 1 at the second constraint, 1 at the third constraint. So together, these variable x3 is there in only one equation, x4 is also in one equation, x5 is also in one equation. So that we get the augmented problem, and the augmented problem is a 5 variable problem with only 3 constraints. So therefore, or in other words, it will be if there are n number of decision variables and m number of different constraints. So total number of variables in the augmented problem will be m plus n, right? And m plus n is the total variables, m is the total number of constraints. So there will be some excess variables. In this case, excess variables are 2. So we have to put them to zeros. So when you put them to zeros, you are going to get what is known as the basic solutions. And these basic solutions will correspond to the corner point solutions of the original point. By using the non-negativity constraints, we can find the feasible solutions from the basic solutions. And we actually know that these basic feasible solutions are one of the basic feasible solution will be the optimum solution, right? So that is what exactly we are going to do. We are for every linear programming problem, we have to write the augmented problem. From the augmented problem, we shall find the basic solution, and from the basic solution, we find the feasible ones, and the basic feasible solutions. One of the basic feasible solution will be our the optimum solution. So this is how exactly we are going to solve the linear programming problems. And in the next class, we shall see how the simplex algorithm is going to be used to solve such kind of problems. All right. So we stop here and thank you very much.